Grasshopper beam engines are beam engines that are pivoted at one end, rather than in the center. Usually the connecting rod to the crankshaft is placed between the piston and the beam's pivot. That is, they use a second-class lever, rather than the usual first-class lever. Origins. The first recorded example of a grasshopper beam was William Murdoch's model steam carriage of 1784. The beam offered negligible mechanical advantage and appears to have been used primarily instead of a crosshead for what was effectively a return connecting rod engine. The American engineer Oliver Evans drew a high-pressure marine grasshopper engine in 1801, and in 1805 built the Orycter Amphibolis, an amphibious dredger. Almost all grasshopper engines placed the crankshaft between the piston and the beam's pivot. This allows a long stroke for the piston, with a shorter stroke for the crank, although with greater force. This was advantageous for early low-pressure steam engines that had limited cylinder force but could increase their power by using a longer cylinder. A few exceptions, those of the Americans Oliver Evans's boats and Phineas Davis's grasshopper locomotives, reversed this and placed the cylinder in between the pivot and crank, a third-class lever. Many grasshopper engines were built as stationary engines. A few notable early steam locomotives used beam engines, all of which were of the grasshopper pattern. Rather more grasshopper engines were built as marine engines. Moraine engines. One of the most important uses for the grasshopper engine was as a marine engine for paddle steamers. After Evans's unsuccessful experiments with the Orycter Amphibolis, the first successful grasshopper engine was that of the first commercially successful steamboat, the P.S. Comet of 1812. In marine use, the grasshopper engine was termed the half-lever engine and used a pair of low-set levers, one each side of the cylinder. This gave a low center of gravity for stability and a high crankshaft, suitable for driving paddle wheels. Comet's engine's designer, Henry Bell, had established her pattern for an engine that would be widely used for paddle steamers over the next half-century. Stationary engines. Unlike the heavy masonry engine house used to support the beam and pivot of a conventional beam engine, the grasshopper beam was pivoted on a swinging link. The crank pan was carried directly by the beam and moved in a straight line vertically, the beam pivot moving slightly sideways on its link to allow this. This simplified the need for a parallel motion linkage on the piston rod. Grasshopper engines were thus lighter than conventional beam engines and could be built completely in factories, rather than requiring considerable erection work to be carried out on site. This encouraged the use of grasshopper engines for smaller-sized engines. Some makers, notably Easton and Amos of Southwark, specialized in such engines. Many were used for pumping, but not for powering large mills. Surviving stationary engines. Stevenson, 1823. Birmingham Museum. Moreland Brewery, Reading. C. 1830. Abingdon. Private collection. Plessey Mill, Northumberland. C. 1830. Pair of engines by Easton and Amos. 1854. Lound Pumping Station, Suffolk. Easton and Amos. 1856. Rootham Park, Barnet. Easton and Amos. 1861. Royal Horticultural Society, Wisley. Later the Royal Albert Hall. Now at the Science Museum. Haywards Heath. 1865. Royal Scottish Museum, Edinburgh. Grasshopper steam locomotives. Puffing Billy, Willem Dilly. 1813. Stourbridge Lion, Agenoria. 1828. Baltimore and Ohio grasshopper locomotives. 1832. Notes. References.